Dilla Liberty. I do programs and communications for the Rangeley Heritage Trust. Tonight, we're welcoming John Meter with the Northern Stars Planetarium to walk us through the night sky. Welcome, John.
Well, thank you, Amanda. It's good to be back again. I'm a little disappointed because I was supposed to be in Rangeley tonight with all you folks and sharing the night sky in a field, all bundled up for the chill, but clear skies, and the skies just didn't cooperate this evening. We don't have clear skies, so we're going to do virtual skies tonight. So I think maybe some of you have done this with me before, but we're going to take a look at the skies of autumn. So let me just go right to that. I like to start off a little bit with the sun. And if you've watched my programs, I often do that. But something a little different tonight was it's now officially fall, as you probably know. You may be more aware of it in Rangeley than I am in Waterville. You usually will head up there with the foliage and all. I bet you it's beautiful. What makes it fall is the way the sun moves. You see the sun moves through the sky. It's actually moving along a path called the ecliptic, which I can put up there as a line like this. Now, technically, it's not actually moving. The Earth revolves around the sun, as we all know. It takes a year to go around the sun. But from our vantage point on the Earth, if you could see the stars behind the sun, and we can turn the arrow so you can see the stars, there are always stars up, even in the daytime. It's just the glare of the sun washes them from our view. So this is sort of an impossible view here. But as we go around the sun, it makes the sun appear to slowly move along this line against the background stars. And the constellations it travels through are the constellations of the zodiac. Well, what does that have to do with the seasons? Well, this path called the ecliptic, which is the path of the sun, is tilted compared to the equator of the Earth. If you could take the Earth's equator and project it into the sky, you would have the celestial equator, which goes from east to west across the sky, this little thin blue line. And when the sun is north of that line on the right side, then it's up more than it's down. And so we have longer days and shorter nights, and we call that the warmer time of the year, the summer season. When it gets below that line, then it's up less, so we have shorter days and longer nights, and then it turns towards the winter side of the season. So you can see right now the sun is just below the equator. Last week, when we had the first day of fall, that's the day the sun is exactly on this line. And that's the only day of the year. There are 2 days of the year, actually, when the sun crosses that line, the first day of fall and the first day of spring. And those are actually the only 2 days of the year the sun sets in the west and rises in the east. Tonight, it did not set in the west. And if we just speed up time a little bit, you can see, let it drop down. And as the Earth rotates, that's what makes the sun cross the sky every day. It goes down, and you can see it's going down a little south of west right there. So the only days it actually sets in the west on the first day of spring and the first day of fall. We're now on the cooler side, the south side of the west. So the days are going to get a little shorter, the nights a little longer, as you're probably well aware. And we're moving towards the winter side of the seasons. So let's take those lines down. We've just set our sun. We are now into autumn. And this is the sky tonight. And right now we're looking at it a little after 7 o'clock, about an hour ago. Let's bring it a little closer to the time we have right now. We're going to zoom ahead here just a little bit. I don't want to go so far that we lose that moon, because we had a nice crescent moon. By the time you get done, if you get outside and it miraculously clears off, the moon will have set. So right now we're around 7:30, and since it is overcast, let's just stop right there, because I want to begin with that moon. The moon right now is crescent, and it moves from night to night. So tomorrow night it won't be here. Tomorrow night it'll be over in here somewhere, and it changes its phase. We have a crescent moon. This is called a waxing crescent. Waxing means it's growing. So tonight that crescent's going to look fairly small. Tomorrow night, it'll be a little bit fatter or thicker. And the night after that, it'll be a little thicker. And after 2 or 3 days, it'll look like a quarter moon, which kind of looks like a half moon, but it's called the first quarter because it's a quarter of the way around its orbit. Well, if you have some binoculars, you might want to check out that moon. So let's zoom in on it. This is about the view you'd get through a decent pair of binoculars. And I like this view a lot. I think it's the best way to look at the moon because you can kind of see the whole thing. You can see that this part that didn't look like it was there really is there. That's just the nighttime side of the moon. So if you're over here, if you were on the moon as an astronaut, the sun would not be in the sky. The Earth would be up there, and the Earth would be big and bright the way the moon can be big and bright in our sky. Only the Earth's bigger and brighter than the moon. So this is the nighttime side of the moon, and this is the daytime side. Now, if you have binoculars and you want to see craters and cool stuff on the moon, the place you want to look is along this line between day and night, because that's when shadows are longest. Next time you're out looking at the sunset, turn around, look back at your shadow. You'll find that you have a big, long shadow. Look at your shadow at 12 noon, and you'll find you have a shadow, but it's a little small one down by your feet. At the end of the day, when the sun's low, your shadows grow. And so craters and mountains cast better shadows, and that gives us contrast at sunrise and sunset. Right here, if you were standing somewhere on this line, you'd be watching the sun come up. It comes up a lot slower on the moon than it does on the Earth, because one day on the moon, the daylight hours last 15 Earth days. And then once it gets dark, the night lasts 15 Earth days. So one day on the moon is the same as one orbit around, almost 30 days. So very long day-night sequences here. But this is where you want to look to see craters. And probably the most distinctive crater you can see tonight is this one right here. That crater's name is Theophilus. And Theophilus is a crater that's about 62, 63 miles in diameter. So for you, if you're in Rangeley, that might be like you going from Rangeley to not quite where I live in near Waterville, maybe to Skowhegan or something like that. Imagine a hole as big as from Rangeley, Maine to Skowhegan, and you got this crater on your hands. The rim around the edge is about 4,000 feet tall. So that means the mountain that makes the rim of the crater is maybe about as tall as Saddleback. You see the dot in the center? That's the center peak. Many craters have that. Craters are made when rocks from space plow into the moon. When they hit, there's a big explosion and stuff goes flying. And just like when you throw a rock in the lake, you get ripples going out. Well, ripples go out too, but they're made of rock and dirt, so they don't disappear like they do in the lake. They just move out till they lose energy. And that creates this circular rim around here, which is a ripple that's as tall as Saddleback Mountain, only it goes all the way around in a circle. The one in the center is a little bit taller. That's a mountain that's about 4,500 feet tall. So that's taller than Saddleback, but not as tall as Mount Katahdin. Pretty big mountain. So if you were on the moon looking towards Saddleback, Saddleback would look slightly smaller than that dot right there. Kind of puts in perspective. Now, these big dark areas you see here, those are not craters. They're called the maria. Each one is a mare. That's an old word which means ocean or sea. Because a long time ago, some people, you often hear them say that people thought those were seas on the moon. But if you start reading old texts, you find that they believed in ancient times that the moon was a perfect sphere and everything in space was supposed to be perfect. There were no bumps. They couldn't see craters because they didn't have the binoculars like you have. The moon was supposed to be this perfect crystalline sphere. And it was believed that these dark seas were the reflection of Earth's seas upon the moon, which was perfect. Well, we now know there's never been any seas on the moon, no seas of water anyway, but these seas were liquid once. They were once lava flows from volcanic eruptions on the moon. The lava came out, filled up the low areas. In some places, it filled big craters like this one over here, which is the Sea of Christes. And then it cooled and hardened, and lava hardens is a very dark colored rock. Neil Armstrong and Buzz Aldrin landed on the moon in the Sea of Tranquility, which is this one right here, right about in here, pretty close to the terminator line. That's the line between day and night. So if you were standing where Neil Armstrong was standing when he, landed on the moon and looked out, at this very moment, he'd be watching the sun come up. Interesting thing to think about. Well, let's back away from the moon. The moon's not going to be out very long tonight because you can see it's very close to the southwestern horizon, and going just a little later, it would set down. But let's look at the stars now. I'm going to back off even a little bit more. And I always like to start with something familiar. And I think for most people, the most familiar group of stars is probably the Big Dipper. Just look a little north of west. So we started off looking at west where the sun went down. We found the moon a little south of there. Just go the other way to the north and you'll find the Big Dipper. 3 stars mark the curved handle and 4 stars mark the pot or the bowl right here. Let's just zoom in on that just a little bit so we can see it better. There we go. So here's the handle, these 3 stars, and here's the pot or the bowl. Now, technically, the Big Dipper is part of a much larger constellation called Ursa Major, the Great Bear. To see a bear, you have to add a few more stars to it. We can draw lines up there, and they draw it kind of like this. Now, if that looks like a bear to you, you're doing better than me. Generally speaking, the handles consider the bear's long tail because you probably know bears have long tails, right? Not. They have short, stubby tails. Well, there are legends all over the world explaining why the bear in the sky has a long tail. I find that interesting. The Dipper plus these 2 stars make up the bear's long body. They draw it down here. I usually draw a line across here instead. And then the nose is out here, and then you see the legs coming down underneath. Sometimes when you look at constellations, they put big ghostly images like this. And I kind of like those. They look kind of neat. The only problem with those is it doesn't really help you learn the stars when you go outside at night, because when you look up, you're never going to see a big ghostly bear floating in the sky. I mean, you're really not going to see blue lines between the stars either, but I think it's easier to visualize the dot to dot drawing than it is a big ghostly animal floating in the sky. But don't worry about the bear. Just find the Big Dipper. Lots of constellations don't really look like what they're supposed to look like, but they might look like something else. And to me, the Big Dipper is enough of the bear that you could just use that. Just know that it's part of Ursa Major, the Great Bear. Now, there are a couple interesting things you might want to find in the Big Dipper if you happen to have a telescope. Go to the tip of the handle. This is a star called Alkaid. And you go under Alkaid, there's a fairly bright star, not as bright as Alkaid. And then take a left and go down to this star right here. This is actually in a different constellation called Canis Venatici, these are the 2 main stars of Canis Venatici, which means the hunting dogs chasing the bear across the sky. And this is technically within that constellation. But if you have a telescope, what you will find if you zoom in on this area is the Whirlpool Galaxy. It's quite beautiful. Let me stop that drift here. Hold on. There we go. This is a galaxy very much like our own Milky Way. We live in a spiral galaxy called the Milky Way. This is a spiral galaxy called the Whirlpool. It was the first galaxy found where they could actually notice the spiral structure. We now know thousands of them. Telescopes weren't as good back in the old days, and it was discovered in the 19th century, sometime in the 1840s, I believe, 1845. Glancing down at my notes here real quick. Now, so this galaxy is 27 million light years away. So a light year, remember, is not really a length of time. It's not a length of time, it's a distance. A light year is the distance a beam of light will travel in a year's time. So a beam of light can travel 186,000 miles in 1 second. So if you go that fast in a straight line for 1 year, you're going to cover a whole lot of miles. That would be 1 light year. Well, a Whirlpool galaxy to us is 27 million light years. That means it took the light 27 million years to get to you. So when you look through a telescope, I mean, here it's just a photograph, but when you're outdoors some night, maybe I get there with my telescope and we all look at the Whirlpool together through the telescope, the light that will enter your eyes when you see this little fuzzy swirl took 27 million years to get to you, which means what you're seeing is not the way it really looks today. It's the way it looked 27 million years ago. When you look into space, the farther something away is, the farther back in time you're looking. So you're really time traveling too. This thing is 87,000 light years across from side to side. And you see this smudge of light up here. Let's get rid of that there. The smudge light, that's a different galaxy. And it collided with the Whirlpool galaxy. I think it was about 70 million years ago. Sounds like a long time, but that's about the same time the dinosaurs died. When galaxies collide, there's no giant explosions because the distance between stars is so great, even though that looks close in. These things are really big, that they kind of go through each other. But the gravitational pull between the stars twists and turns the galaxies, and it stirs it up. And if you look, you see lots of little pink patches. Those are big clouds of hydrogen gas. They're called hydrogen 2 gas clouds or emission nebula. Those are places where stars will be born. Stars are made of hydrogen. And when these clouds form and get stirred up, they get excited and they start glowing in this pink light. And in a few million years, each one of these little pink patches will turn into several hundred stars. We find these pink patches scattered through our own Milky Way. And I'm going to show you one in a few minutes. So this is the Whirlpool Galaxy, one of my favorite ones to look at. And this galaxy here, which collided with a whirlpool 70 million years ago, is now moving away from it and away from us at about 300 miles per second. So they're really zipping apart, at least on our sense of speed. For something this big, that's really not all that fast. And that's kind of right underneath the tip of the handle of the Big Dipper. So that's a galaxy. Now we live in a galaxy called the Milky Way. We're going to get to that in just a couple minutes. Once you found the Big Dipper and the Great Bear, if you like, and maybe even the 2 hunting dogs down here, now go to the back 2 stars of the Big Dipper's pot. They're called the pointer stars because if you draw a line up through them, their names are Merrick and Doobie. So you go from Merrick to Doobie, then you doobie, 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 right across the sky. You'll come to the most famous star in the whole sky, this one. That's Polaris, the North Star. It's not the brightest star. There are 45 other stars brighter than Polaris. It's famous because, as you can see, it's directly above the Earth's North Pole. So if you draw the closest line from the North Star to the horizon, it'll always point you due north. You can use it like a compass. That's why it's famous, not because it's bright. It also marks the end of the handle of the Little Dipper. The Little Dipper's handle looks like it's bent around backwards, and there's the little pot. And it's also known as Ursa Minor, the little bear. So we have Canis Vernatici, Ursa Major, and Ursa Minor. And if you want, we can, just for the fun of it, put some ghostly images up there to see a way people imagine it. I don't know how you take 2 stars and make it into two dogs, but, you know, little imagination goes a long way. Let's get back to our dot top. Well, go from the Big Dipper to the Little Dipper and go right past it. Bend a little to the right, you'll find a W in the stars. And it looks kind of like a W, or if you look at it the other way around, maybe like an M. That's Cassiopeia the Queen. Now, most people agree W's don't look much like queens, but it does look like something a queen might wear. I like to imagine it as the queen's 3-pointed crown. And there's the base of the crown where she would put her head right there. Now, traditionally, it is drawn as the queen sitting on her throne. So she is drawn something like this. Now, if you turn that zigzag into a lady sitting in a chair, staring at herself in a mirror, you're doing better than me. But that's the way you'll see her drawn in many, many books, and many, many apps on computers. I still like the idea of a crown better. Now, you got to be careful with your crowns, because to me, that looks like a queen's crown. But if we come back over here to the Big Dipper for a moment, over just the other side of the handle, we find another little half circle. This is called Corona Borealis, which means the northern crown. This one looks more like a tiara, like a princess would wear. So this is the northern crown. The bright star's name is Gemma. And Gemma is the brightest star in the crown. And since crowns are covered with gems, it seems like an appropriate name. In the center of Gemma, you can see a little faint star right there. Let's zoom in so you can see this star. That one right there. Now that star right there is kind of a special star. It's called, hold on just a second, make sure I get it right. Yeah, it's called R-Core Bohr. So it's just designated by the name R. Core Bohr stands for Corona Borealis, the northern crown. Now, what's special about the star is it shows up pretty easily with your eyes if you're in a nice dark spot like you might have in Rangeley, because you have great dark skies up there. I'm a little jealous. And if you can't see with your eyes, take a pair of binoculars, it'll show up most of the time. It's a star that's about 4,500 light years away, and it's right on the edge. It's around 6 magnitude, which means it's about as faint as you can see without it being so faint it disappears on you. Except for on occasion, it does disappear. Every so often, it just disappears, and it'll disappear for maybe a year, and then it comes back again. It drops down to 15th magnitude. 6th magnitude is as deep, as dark as you, as faint as you can see without a telescope or something. And to see it at 15th magnitude, you need a really big telescope, not something someone would have in their backyard. So I always go out when I look at that northern crown, I always look to see if I can see our core bore. And I've never not seen it. It's always been there, but it does periodically just disappear from view. So now come back over here to the Queen's Crown. And by the way, that's not the only crown. We've got the Queen's Crown, Cassiopeia, the Northern Crown, Corona Borealis. But in July, way down on the southern horizons, another little half circle, and that was the Southern Crown. So I guess you really need to keep your crown straight. Come over to Cassiopeia, and you see the W shape. Go to the end of that W and go right up above it, right up about in here. You're actually in the constellation of Cepheus the King, the blockhead king. He does have a square blockhead here with a pointed crown like a dunce cap. We'll get to why in a minute. But what I want you to see here is this little reddish patch. Now, you can see, if you look around here, a whole bunch of reddish patches. Some show up really well and some don't. This one shows up fairly well, whereas this big one is so diffuse, you won't see it unless you take a photograph. This one, though, might show up in a backyard scope. It's called the Cave Nebula because of this dark thing. Looks like a cave going in. Though I've had some kids tell me it looks like a big bear with two big bear ears here, like he's walking, coming at you. That's a little more ominous looking to me. It's referred to as the Cave Nebula. You remember the little red, pink spots we saw in that whirlpool galaxy? Well, this is one in our galaxy. This is a place where stars are forming. This is all hydrogen gas. Now, the gas just floating in space isn't going to glow like this unless something gives it energy to glow. But this hydrogen is collapsing on itself. And when it collapses, each clump starts to build up. And as it builds up, it has more gravity. So it pulls more gas in and it builds up and gets more gravity. And as there gets to be enough, there's so much pressure builds up in the center that it causes fusion to happen in the center of each of those clumps. And when that happens, that clump becomes a star. So all these stars you see in the midst here are all young stars. These are stars that form from this cloud. This cloud is big enough to maybe make 300 or 400 stars the size of our sun, and it's already made quite a few, as you can see. And so when they start shining, they give off a lot of ultraviolet light. And the ultraviolet light, the remaining hydrogen is stimulated by it and it makes it glow with the red light. So you can see this is glowing with red light, stimulated by the light of the stars that form from its own cloud, which is kind of interesting. These dark regions are absorption nebulas. That's where they're big clouds of dust. They're blocking the light from the nebulosity behind it. So we're seeing two different kinds of nebula here. The emission nebula, which is the red, and the black is an absorption nebula, something that's dark and just absorbing the light. It's not glowing at all. It's blocking the light from what's around it. So this is one of those emission nebulas like we saw so many in the whirlpool. The Milky Way has them too, and this is a really nice example of one right here. And it's right next to Cassiopeia and King Cepheus, the king and queen of Ethiopia in mythology. And they have a daughter named Andromeda. Now, what happened in mythology is Queen Cassiopeia was very vain, and she bragged a lot about her beauty. And one day, and I'm really simplifying this story, she made the claim that she, while she was busy looking in the mirror, thought she was especially beautiful, even more beautiful than the sea nymphs. Well, the sea nymphs were like mermaids, and they heard her and weren't very happy. So they went to Poseidon, the king of the sea, and complained. And he, of course, sicked a sea monster on their kingdom, Cetus the whale. And he was destroying the kingdom. So King Cepheus went to the oracle, the wise man of the day, and said, what can we do that you can't stop the sea monster? And the oracle said, your wife compared herself to the sea nymphs, and you just don't do that. The only way the whale will stop is your wife has to sacrifice the only thing she loves more than herself. And that, of course, was her beautiful daughter, Andromeda. Andromeda's right underneath here. She's kind of lying down. This is her head. She has a body, kind of a triangle in these stars right here. Then a leg here. And a leg there. And if you look carefully, this little line of stars, I imagine, is the hem of her dress. Now come back up her body, and this little line of stars is an arm, and this little line is her other arm. Now, that's the way I draw it. I wish I could put lines up there because I think it makes a pretty good dot to dot girl laying there in the sky. They don't quite draw her that way. They just draw one side of her body and her belt. They don't put the arms in or her other leg. Go figure. I don't know why, but they didn't ask me. So this is Andromeda the princess. So she was chained to a rock to be eaten by the sea monster, by her blockhead dad, King Cepheus. So not only does he have a square block head and a dunce cap, because I think anyone who chains his daughter to a rock to be eaten by a sea monster is definitely a blockhead dad. But he did that. Now, of course, she does not get eaten. She gets saved by Perseus, the hero. He's right down here. To see Perseus, his head is up here. I usually make a little triangle here for those would be his shoulders. And then he's got his two legs coming down here. And I often draw a line over here and have this little circle be the head of Medusa, because he slayed Medusa. Medusa was the creature with snakes instead of hair, who was so ugly that if you looked at her, you would turn to stone. So he's always drawn holding Medusa's head. So you got two legs here and a head at the top. Kind of imagine the rest here. Sometimes they come down here and they use these two stars to be the eyes of Medusa, and they put Medusa on this side. I think that's what they do in this picture. Let's bring it up and see how they did it that way here. They draw it both ways. You'll see it drawn many different ways. This star right here, the brighter one of the two eyes, is called Algol, which means the demon star, which seems somewhat appropriate for the Medusa's head, which will turn you to stone. It's also famous because it changes brightness. We saw the Arcor boar, which gets so dim it disappears. This one never disappears, but it'll go so it's fainter than the other eye and then much brighter than the other eye. And it changes every 3.5 days. So it's constantly changing its brightness. It's a variable star. So we have quite a story up here. Perseus is flying back after slaying the Medusa, and he looks down and sees this beautiful young lady chained to a rock, and he swoops down and pulls out the head and turns the sea monster to stone and rescues her. A real simplification of the story, but that's kind of the deal. So we see a royal family up here and a hero beside. If you look up at King Cepheus, we saw a place here just a moment ago between the two, the cave nebula where stars are being born. Underneath his chin, remember this is his crown, so he's kind of sideways in the sky, so his chin's on this side. You can see a pinkish reddish star right here. And if you have a pair of binoculars, it'll turn much redder. If you have binoculars, it'll turn redder than it looks here. Have a telescope, it'll turn even redder than it looks here. Here it looks kind of orange. When I've looked at it, it looks almost blood red. It's a beautiful star. This is called the Garnet Star. And the Garnet Star is one of my favorites to look at. I think it's a very beautiful star. And it's a very old star. This star is 1,000 times bigger in diameter than the sun. So this is a red supergiant star. And it's near the end of its life. So this star is one of those few stars, like Betelgeuse in the wintertime or Antares in the summertime, that may explode at some point in a supernova explosion. So this is a very big old star and a really cool one to check out if you have a chance to. And it's underneath the chin of King Cepheus, the blockhead king. Now come down to the princess, because the princess is the star of the show. Because if you go down just the way they draw it and go up the princess's belt, just above her belt, you may have noticed it looks like a fuzzy patch of light right in there. Well, that is the Andromeda galaxy. This is another galaxy. This one is not nearly as far away as the whirlpool. The whirlpool you will not see without a telescope. This one, if you're in a dark spot and look at the night sky, you can see this with just your eyes. It'll look like a very faint star. You can just barely see it if you know where to look. Lots of times to see it, if we zoom back, you'll find that if you stare at it, not here on the screen, but outdoors, it'll seem like it disappears. So you have to stare back at one of these two stars. Now, the corner of your eye, you'll see it. That's the trick of your eyes. The part of your eyes that sees faint light the best is not in the center, it's around the edge. So for faint things, you don't look right at them. Now, if you have binoculars and you zoom in like we did, and we'll do it one more time, it'll look like this, kind of a fuzzy patch of light. Well, this is the Andromeda galaxy, and it's a little bit bigger than our Milky Way. A spiral, just like the whirlpool, but we're not looking straight down at it like we did the whirlpool. This one, we're looking at it about a 45-degree angle. Now, with just your binoculars, it's going to look like a fuzzy patch. Binoculars aren't strong enough to differentiate the stars. But if you have a bigger telescope or you take a photograph of it, it'll look like this. And this is much more like what you'd see in any photograph of the Andromeda galaxy. It takes a pretty good telescope to see this through the telescope. But even a medium-sized telescope, it'll look kind of fuzzy. You might see a few hints of stars. When you take photographs, the camera can gather light over time and bring in detail your eyes just can't see. So this is the Andromeda galaxy, and it's coming at us. Remember, we saw how the whirlpool and that other one collided 70 million years ago? Well, in a few billion years, the Andromeda galaxy is going to collide with our own Milky Way galaxy. And they may swirl together and turn into one giant galaxy, or they may just distort each other and then go flying off in different directions like they did in the whirlpool. And you know how the Earth has the moon going around it, like we saw earlier, and the sun has planets going around it. Many galaxies have little galaxies going around it. Andromeda has two. This one right here, this is a small satellite galaxy that slowly orbits the big one. And this is another one right here. It looks like a star, but it's actually a slightly smaller satellite galaxy. So this has two little satellite galaxies going around it. And the Milky Way has two as well. If you're in Australia or South America, you can look up in the night sky and see them. They're called the Large and Small Magellanic Clouds. They look like chunks of the Milky Way floating off to the side, but they're actually two satellite galaxies. Well, that's the most distant spot of light you can see without a telescope. It looked like a little faint spot of light. Now, one thing I do with my binoculars to see how clear it really is and how dark the sky really is about the same distance below Andromeda. Right in here, there's another galaxy. This one's called M33. And with binoculars, it looks very, very faint. And I can see it because I know what I'm looking for. It's right here. I don't know if you can pick it up or not. There's a faint, fuzzy patch of light that you can just barely see. And you can get so you can see that with your eyes by kind of looking around with the binoculars. It won't look much different than it does here, unless, of course, you have a bigger telescope or you take a picture of it. And then, of course, it's going to look like this. This is another spiral galaxy. So there's spiral galaxies, as I said, all over the sky. And you see some hydrogen clouds here of star formation, just like we saw with the Cave Nebula a few minutes ago. This one's a little bit further away than the one we just saw. M33, I forget its distance now, but it's about twice as far away. It's larger, but it's very diffuse, so it barely shows up in the night sky. But it's a good test of the sky because it has to be a really clear, dark sky to pull that out with a pair of binoculars. So we have quite a sky here. Now, when Perseus came to save Andromeda, he wasn't just like flying to the sky like Superman. Of course not. That's ridiculous, right? No, he was riding on the back of a flying horse named Pegasus. And to see Pegasus, the head of Andromeda is one corner of a great square in the sky known as the Great Square of Pegasus. Now, Pegasus actually only uses these three stars, but we always make the Great Square. So to see this flying horse, which is the horse that Perseus rode in mythology, this is the back of the horse. It's flying upside down. You can do that in space, remember. This is the back of the horse. Here's the horse's neck with his head. Come back down his head and down his neck. Here's the chest of the horse and two front legs going out in front. There's no hind legs, and there's no tail, and you can't see the wings either. Although I had a friend tell me that he always liked to pretend this little zigzag of stars in the middle might be one of the wings. I've never seen it drawn that way, but you make it up so it works in your head. So just think of it as the chest of a horse, the bust of a horse, and he's like leaping across the sky. Though in mythology, he always has wings. Well, once you find the Great Square of Pegasus, that stands out nice and clear, you can find this horse, the neck and the head. And remember, this corner here is actually the head of Andromeda, the princess. Well, I want you to go to the tip of the nose right here. This is a star named Enif. And Enif is the end of the nose, and kids always say, oh, that's because he sniffs or something. I don't think the name is really derived from sniffing, but it kind of sounds like that with Enif, like he's Enifed enough. Well, go to the tip of that, and right over in here, with your binoculars or with a telescope, you're going to see, oh, that's close right here. That was close. It's always kind of hard to see till you get in close. A kind of cluster called a globular cluster. And globular clusters are very beautiful, and they're densely packed regions of stars. Our galaxy has about 150 of these, and they form a halo around the main galaxy almost. And we find other galaxies have them too, so they're very common, and they tend to be made of very, very old stars. This one is called M15. What you keep hearing, you may notice I keep referring to M numbers. This is a catalog of deep sky objects called the Messier catalog, named after Charles Messier. Charles Messier didn't care about these objects. He was a comet hunter in the 1700s. And telescopes back then, most of these things looked like fuzzy patches of light. He didn't know a globular cluster from a galaxy. They were just fuzzy patches in the sky. And when you find comets, they kind of look like fuzzy patches too. But comets move, and they don't stay here. They come, they get bright, then they fade away and disappear. These things stay in the same spot, but you don't see them move. You see them move over many nights, the comets, that is. So he cataloged all the objects that didn't move, and they all got a Messier number. So this is M15, Messier 15. One of the things he wanted to avoid, confusing, thinking it might be a comet. He didn't want to waste time doing that. We still use the numbers, but we're more interested in these objects now. So this is a globular cluster, and there's 100,000 stars in this, 100,000. And it's 33,900 light years away. And width-wise, from here to here, is about 180 light years. So it's a pretty big object. And these are very old stars. You can see a lot of little red stars here. Stars tend to turn red as they get older. And we tell the age of a star by their spectrum. Put the light through a prism and you get a rainbow from the light, which scientists call a spectrum. And if you spread that out, you find little lines. Those lines are created by different elements. If it's a young star, you only have the lines created by hydrogen, just two or three lines. But if you're an old star, you might have hundreds of lines because there'd be hydrogen and helium and lithium and carbon and all kinds of different things. And a lot of these stars have lots of lines, which tells us they are very, very old. So this is one of the older globular clusters. This is actually believed to be over 12 billion years old. And there's 100,000 stars here. And that's right off the nose of Cygnus, not Cygnus, of Pegasus, the flying horse. So we're finding some interesting things in the sky here. Now, right, if we keep right on going, we see our own galaxy, the Milky Way, crossing the sky here. So the moon, which we started with, is right down here to the southwest, just to the west of the Milky Way. So this is our galaxy. Now, if did you see how the sky just changed? I changed it to more the way it might look for you in Rangeley than the way it would look for me living here outside of Waterville. If we go back to the skies of Waterville, you see not quite so many stars, do you? And the Milky Way is a place where it really helps to be in a dark spot like Rangeley or up near Greenville, the AMC properties up there, or Katahdin Woods and Waters or Baxter State Park or someplace. You go to all those special spots like where you are, and you see the stars better because the skies are darker and there's less light pollution. So let's go to where you are, and you'll see the Milky Way brings out lots of detail in it. Now, the galaxies we've seen so far, we've been looking kind of face on. Remember, they're round like plates, and that's how the spiral arms go. But if you tip them up edge, they're flat like plates too. They've got a little thickness to them, but they're not round like a ball. They're shaped like a frisbee or a plate. And we're inside the Milky Way. All these stars over here and all the stars over here, both on east and west of it, that part of the Milky Way too. Now, we can find galaxies like we've seen, like M33 or Andromeda or the Whirlpool. They're not in the Milky Way. We're looking out through the Milky Way to other galaxies. But all the clusters we've seen, the globular cluster, that the stars we've seen, like the Garnet star, they're all in the Milky Way. When we look at this band, we're looking in towards the center of our galaxy. And there's a lot more stars in towards the center. And the actual center is right down in this region, right down here. Now, we only see part of the center because it goes below the horizon. But what we could do if we wanted, don't anyone leave the room because we're going to hop out into space and get away from the Earth. And get away from it, we can see the whole thing. So let's take that moon down too, like we're really floating in space. Now you can see the whole Milky Way. The center is right here. You see it kind of bulges in the middle. Then the spiral arms go out from there. And this would be one spiral arm going this way and one going off the other way. We live in an arm called the Orion arm. So this is the whole Milky Way as if the Earth weren't in the way. Well, let's come back down to the ground because as beautiful as this is, I kind of like being on the Earth. We'll put the directions up to keep us oriented here a little bit. Now let's bring the moon back up too. And all the planets. There we go. So that's our galaxy. And right in the middle of the galaxy, we have three stars that really stand out from summer through till about Christmas. That means for 2 seasons, almost the entire summer. They first appear in June and they don't disappear till the end of December. It's called the Summer Triangle. And it's constituted with 3 stars. The brightest star is called Vega, then Deneb, then Altair. See that big triangle? That's the Summer Triangle, which lasts all fall. Now, that's not a constellation. They're just 3 bright stars. When we make pictures that aren't the official constellations like the Big Dipper or the Summer Triangle, we call them asterisms, which is sort of like easier things to find than some of the constellations sometimes. Well, each one of these 3 stars has its own constellation. And I think the easiest one to see is the top one with Deneb. Deneb is an Arabic word which means tail. And it's the tail of Cygnus the swan. So let's zoom in and see if we can see this swan here. Let's get rid of the nebulosity for a second because you won't see that without a telescope. So here's the swan's tail. Draw a line to Satyr, this star. And rather than just drawing a line, I draw an oval between the two because that's the swan's body. This is his tail. This is his shoulder. Swans are big birds. We'll give them some heft. We got a big wing coming way off here and back to the tail like that. He's flying. Then another wing on the other side coming way over to this star, then back to the tail like that. Come back up to the shoulder, and there's a long neck with a head right there. So let's put some lines on him. And they don't connect the wings back to the tail like I like to, but you can still get the sense of a swan flying across the sky. Draw him like this if you want. So this is Cygnus the swan. He's flying right down the Milky Way. And that star I clicked on which marks the head of the swan, that's one of my favorite stars. It's a star called Alberio. Now, I've shown you one star close, the Garnet star, which was bright red. Now, I always point out Alberio. Kids ask me if I have a favorite star, and this might be it. It doesn't look all that special, but when you zoom in on it, what happens is it splits into 2. Well, that's not uncommon. About half the stars you see are actually more than one star. What makes Alberio special, and it doesn't show up in this program very well, is that they're 2 different colors. The smaller one is blue, and the blue will stand, and when you look through a telescope, stands out really clearly, whereas this one's an orangish color. You can kind of get a little hint of it here, but it really shows up much better through a scope than it does in this program. So we get a binary star, meaning we believe they probably orbit each other, though these 2, we've never seen evidence of them moving. So if they do orbit, it may be thousands of years before they make a complete orbit around each other. But they are 2 distinct colors. And you only see that with a telescope. Even binoculars won't split them up because they're so far away. And I don't know exactly off my head exactly how far away Alberio is, but it's quite a ways away. And if you don't have a telescope and you want to see something similar, go to this side of the wing, and this star right here, whoops, I'm sorry, I didn't mean to the program does that automatically. I call this the poor man's Alberio, because when you look at that star with a pair of binoculars, you can easily split it, and it's got kind of the same coloration, an orange one and a blue one off to the side right here. They're not nearly so close together, so with just binoculars, you can split that pair. And that's not too hard to find. If you can find the swan, and this is Deneb the tail, go halfway down this wing, you're going to see those 2 bright stars, and it's the inner star right there. Now, so we have our Milky Way right here in the sky. Crossing the sky, goes all the way back through Cassiopeia. You can see Cassiopeia, the queen, right there. And here's Pegasus, the flying horse, Andromeda and Pegasus, the great square Pegasus and the flying horse. And if we back off a little more, you can see almost everything we've looked at here tonight. So there's the hero, Perseus, the hero. And over here's the blockhead king right there. And there's the princess. Put up the fancy drawing so you can imagine them a little bit better. Vega, the brightest star of the summer triangle, is in Lyra the harp, as you can see drawn here. It's just this little parallelogram connected with Vega on one side, like a spring just broke and it went zinging out. That's supposed to be a harp. So we got quite a combination of constellations here in the eastern sky. If we swing around back to the north, then of course we can find Ursa Major, the Big Dipper, and Ursa Minor, the Little Dipper, and the North Star right at the end of the handle. And if we swing all the way around to the west, we come right back around and there's the moon right over here. And he's seen quite a few interesting things in the sky tonight. But we're not done. There's two more things I want to show you, which I think are really worth looking for. So let's swing right around to the south, the other side of the Milky Way, and look down low underneath Pegasus, and you're going to see a very bright star tonight. And you'll see it tomorrow night too. It's over in the southeast. It's this one right here. You won't miss it. And the reason you won't miss it is because, first of all, it's not a star. It's the planet Jupiter. So let's just shut the lines off for a second and look in the southeast, fairly low down, and you're going to see the brightest star in that part of the sky will be Jupiter. Now, Jupiter right now is as bright as it will be for almost all of us, unless you're maybe 10 years old. Then you might see it this bright again someday. Jupiter's brightness and all planets' brightness vary a little bit depending on where they are in their orbit compared to where we are in our orbit. And right now, the combination of things makes Jupiter the brightest it's going to be for the next 70 years. It's always fairly bright. It's not going to ever disappear on us, but it's exceptionally bright because it's exceptionally close right now. Its orbit, like all the planets, they go around the sun, not in circles, but in ovals called ellipses. And it was just at opposition, which means it's just opposite us, as close to us as we can get it in the sky. And it happened to be at the point of its oval orbit where it's also closest to the sun at the same time. So that means its distance away is the least it's been in my entire lifetime. And I don't think I'll get to see it this close again, unless I live to be 135 or 40 years old. I kind of doubt that probably, but who knows? Maybe technology does strange things, right? Well, when you have that, if you have some binoculars, or better, if you have a telescope, you definitely want to check out Jupiter. Jupiter is the biggest planet. We zoom in on it. What you'll see with your binoculars will be something kind of like this. You'll see Jupiter, and you can see up to 4 little dots. Here we can see 1, 2, 3 on one side and 1 on the other. That's the way they are tonight. And those are moons. Here they look as big as Jupiter. They'll look smaller than Jupiter. This is a function of the program. They'll look small, but they'll look like little stars in a row. Tonight's 3 on one side and 1 on the other. Tomorrow night, there may be a different configuration. We can check that out if you want to here in a moment. So if you have a telescope, you get in close and you see everything a little better. You'll see these dark brown lines, though in most telescopes, they're going to look gray. You have to remember, unless this light is strong, like the light of a star, like in the Alberio or the Garnet star, then the light shows up. If the light's not super strong, then the part of our eyes that sees it around the edges is colorblind. So it's going to look either gray or white or black. So you're not going to see much color on Jupiter unless you have a camera. But you will see these 2 dark lines. Those are cloud bands. The wind on Jupiter blows over 100 miles an hour. In one band, it'll blow west, and the next band, it goes east, and the next band, it goes west, and back and forth, stretching the clouds in these long bands. Now, Jupiter has no ground, so no one's ever going to land a spaceship on it. You can't put rovers on Jupiter like we put rovers on Mars. Not going to work. There's no ground to land on. It's all clouds and gases and liquids inside. If you fly into it, you won't come out the other side because you're going to get crushed by the weight of that atmosphere. And then what's left of you will melt and disintegrate because the center is so hot. Don't fly into Jupiter. This planet's 1,000 times larger than the Earth in volume. And these are the 4 large Galilean moons, named after Galileo, who first saw them with his telescope. Jupiter actually has at least 79 moons going around it. But with the backyard scope, you're only going to see these 4, because it has 4 big ones and 75 little tiny ones. Now, if you want to see how it would move for tomorrow night, let's lock that in. And let's just jump ahead We'll see how it goes. So this is the way it looks tonight. Tomorrow night, that's the configuration. 1, 2, 3. So one's probably behind Jupiter because it doesn't show up, does it? Go the next night. You see that they move pretty rapidly from night to night as we jump ahead through the days. There's 4, 2 on this side and 2 on that side. Well, let's come back to today. We don't want to leave you in the future. Gives you an idea, though. Well, there's one more planet, and I'd like to leave you with my favorite. So let's come all the way back to Earth, and we see Jupiter shining very brightly. But if we look off to the east or towards the south from there, you're going to see another fairly bright star, the brightest star in this region, not quite as bright as Jupiter. This one right here, right there. That's our second planet that's going to be visible tonight. And that one is Saturn. If you want to see Saturn's rings, you need a telescope. With your eyes, it's going to look like a mediumly bright star. With binoculars, it might look kind of oval shaped, but you won't distinctly see rings. To see those rings, you definitely need to have a telescope. And with a telescope, they'll start to show up, kind of like this. Now, it's not going to be as big as the pictures you see in magazines. Those pictures you see in magazines were taken by probes like the Cassini probe that went to Saturn and orbited Saturn for many years, or the Voyager probes that flew by and took up close pictures. With a telescope, it always looks smaller, but people are always amazed how clear and crisp those rings look. Let's zoom in a little bit more, like we're magnifying more. These dots around it are moons. You almost always see this moon. That's the largest one. That's Titan. Titan is the largest moon in the second largest moon in the solar system. Excuse me. It's bigger than the planet Mercury. Kids often ask me, why isn't it a planet if it's bigger than one of the planets? Well, planets go around stars. Mercury orbits the sun. Moons go around planets. Titan's a moon because it doesn't go around the sun. It goes around Saturn. So it's a moon, even though it's bigger than one of the planets. It's about what they orbit, not how large they are. Saturn itself is 700 times bigger than the Earth. It's made of clouds and gases, so you can't land there either. Kids always want to know, can you land on the rings? Well, the rings are made of ice, mostly water ice. So if you took a chunk of Saturn's rings and melted it, theoretically, you could drink it, though it's ice frozen down to about 300 degrees below zero. So it's really cold, and it'd be as hard as a piece of granite. Now, this is not a sheet of ice. It's not like a frozen lake, so you can't put on your skates and land there and wear a spacesuit and go skating around Saturn. It's chunks of ice no bigger than the biggest chunks. There might be some as big as you or me. Most of them are smaller than your fist. A lot of them are the size of crushed ice, like you put in a soft drink in the summertime when it's hot, which it isn't tonight. But you know what I mean, that crushed ice. A lot of it's no bigger than that. Now, these rings from the inside edge here to the outside edge, that's 45 to 50,000 miles, depending on where you measure it. That's a long way, 45,000 miles. But if you measure the thickness from top to bottom, that varies too. The thickest spots might be a mile thick, but most of the places it's not that thick. The average thickness from top to bottom is about 80 yards. 80 yards. That's like if you could tip Saturn up on edge and bring the rings down to the 50-yard line of the Super Bowl, the rings, for the most part, would fit between the goalposts, and it'd extend 45 to 50,000 miles into the sky. Wouldn't that be a halftime show? Well, since they're frozen to 300 degrees below zero, they're very cold, and they'd freeze everyone solid in the stadium, kind of end the game right there. We wouldn't want to do that, but it's an interesting thing to think about nevertheless. So there you have it. There's a little tour of the sky and some of the things you can see outside tonight. And everything will be there tomorrow night. The only difference is the moon won't be here. If we lock on the moon and jump that ahead, I'll show you where it'll be tomorrow night. We'll finish with this. Let's just bring our clock up here and go to October 1st. And you see tomorrow night, it's going to be right in the middle of the Milky Way. And you see how that got a little bit thicker. Go ahead the next day, it's on the other side. And so on. That's how far it moves from day to day in its orbit around the sun. And now you see it's getting bigger. So its phase changes from day to day, and it's always moving eastward across the sky from one day to the next. All right. Well, I hope you've enjoyed this tonight. If anyone has any questions, I'm going to stop sharing here.